Wow, these are some great looking histograms. If you watched my earlier videos, you are probably sick and tired of looking at them. So let's get right to the point. Greetings folks, welcome. There are a variety of statistics that we can use to describe the spread of a variable. We cover the range and interquartile range in a different video, and in this video we'll look at the variance and the standard deviation. The standard deviation is important because it is often used to describe the spread of a histogram with a symmetric shape. The variance measures the extent to which observations are different than the mean. If all the observations are very close to the mean, the variance will be small. If the values vary quite a bit from the mean, the variance will be large. The notation that we use for the variance is s squared for a sample variance and sigma squared for a population variance. Here's a formula for a sample variance. So the notation x bar represents the mean of the sample, and the lowercase n represents the sample size. Here's a formula for a population variance. So the notation mu represents the mean of a population, and the uppercase N represents the size of the population. Going back to the formula for the variance of a sample, the top part of the formula measures the extent to which all the values of the variables, these are the xi's, differ from the mean, which is x bar. If all the values of the variable are very close to the mean, the top part of the formula would have a small value, and the variance would be small. If the variable has values that are all over the place, the difference between the xi's and the mean would be large, and this would give us a very large variance. If you have a sample with 4 observations, the top part of the formula translates into the value of the first observation minus the mean, which is x bar, and you square that, plus the value of the second observation, which is x2, minus the mean, again x bar, and you square that, plus the value of the third observation, which is x3, minus the mean value, and you square that, plus the value of the fourth observation, which is x4, minus the mean value, and then you square that. If the values in our data set are 17, 21, 22, and 24, which has a mean of 21, it looks like this. So at the very top of the formula, you have 17 minus 21, and you square that. Then you have 21 minus 21, which is 0, and you square that. Then you have 22 minus 21, which is 1, you square that. Then you have 24 minus 21, which is 3, and you square that, and you add those values. You divide that by n minus 1, and it gives you a variance of 8.67. As was the case with the mean value, which we can sometimes use as a measure of the center of the distribution, the variance is not resistant to outliers. In other words, outliers influence the variance. Let's say we add just one observation to our data set, who happens to be a 72-year-old. If we add this one person, which is an outlier, it increases the variance to 22.95. So heck, the variance went from 8.67 to 22.95 when we just added one person. The variance is certainly a pretty cool statistic that we could use to describe the spread of a variable, but it's a little bit hard to interpret. The reason for this is because the variance is measured in terms of the unit of the variable squared. From our earlier example, we got a variance of 8.67, which is measured in years squared. And it's not common to think about someone's age in years squared. Sometimes you might want to convert your age into dog years, but you would never say, I am this many years squared. So instead of using the variance, people often use a closely related statistic called the standard deviation. The standard deviation is the square root of the variance, which means that it's expressed in the same units as the variable itself. If you have a variable that's measured in dollars, the standard deviation is measured in dollars too. Going back to our original data set, which had a variance of 8.67, the standard deviation is 2.94 years, which is the square root of the variance that we found. Just like we learned for the variance, the standard deviation is also influenced by outliers. For this reason, we use the 5-number summary, which is the minimum, first quartile, median, third quartile, and maximum value to describe the center and spread of a skewed distribution. But if you have a symmetric distribution, we can use the mean as a measure of the center and the standard deviation to describe the spread of the distribution. In a different video, I will show you how to calculate the variance and standard deviation using Excel, but for now, let's just look at the Excel formulas. Let's say you have a variable that's in cells B2 to B501. For the variance, it could be VAR period S, then parenthesis, then B2 colon B501, close parenthesis. That S is telling Excel it's the variance of a sample. If you want to do a population variance, it would be VAR period P, and then parenthesis, B2 colon B501, close parenthesis. Or you could just use plain old VAR parenthesis B2 colon B501 parenthesis, which is the same as the variance for a sample. In most applications, you're dealing with just a sample of data, so you can use that VAR formula without specifying whether it's a sample or a population. For the standard deviation, the formula is STDEV period S. Can you guess what the S stands for? Yeah, it's sample. And then you put in a parenthesis B2 colon B501. Again, this is just if your data happens to be 500 observations in the cells B2 through B501. I just use this as an example because I like to say B2. If you want to calculate the standard deviation of a population, it would be STDEV dot P, and then you'd put in the range of data. And then finally, just the plain old standard deviation formula in Excel is STDEV, and then you put in the range of data surrounded by your parentheses, which is the same as STDEV dot S. So sort of the default in Excel is that they assume that you're working with a sample data, which is, again, the most common application when you're doing data analysis.